Now this chapter only have 2 sections, so we'll go to section 2, 10.2. It's just basically now generalized to high dimension, and so they becomes PDE. It can if you keep generalizing, you can actually get the not just the spatial operator, you can get to the temporal operator also on a green function with both space in both space and time. That is also possible. But for this section, the textbook stay with differential operator like divergence, Laplacian, and that kind of thing, right? And the corresponding form for 3D for the self-adjoint problem. This one. So for 3D, so your Laplacian psi as function of is given by, instead of a single derivative, you have divergence of function p depends on x, and then the gradient of psi. The hex we use R, it doesn't matter. That's QR. And now the inhomogeneous system also a function of space. Now this is a 3-dimensional problem. So again, the boundary value will be depends on your regions or your domain of the problem. So sometimes you consider a volume, a certain volume with that has a surface. You can consider the interior problem inside this volume and outside of the volume. Outside, you need a boundary condition at infinity also. But anyway, and then again the boundary condition on S can be Dirichlet. You specify psi, and like this, you require psi to be 0 on the boundary, or the Neumann or partial psi, partial n, 0. For Neumann, if define your n direction perpendicular to the surface. Okay, those are the generalization to 3D, right? And again, with the self-adjoint form, you have the property that we just mentioned, the G. You found a G. I should say, you write down your solution as a form of the green function. In this case, it's a 3-dimensional integration. You have G. I think your textbook using also. Also one, whatever. Yeah, it's house of 1 and house of 2. Well, it doesn't matter, house of 1, house of 2. And then F depends on house of 2. And integrate house of 1. That should be a 3-dimensional integration over the volume. Okay, and that should be the form of your solution. With the inhomogeneous term F, you put this is an arbitrary inhomogeneous term. The F, any F, you put it here, and require the corresponding boundary condition satisfied by the G function. And for the self-adjoint form, we can again use the eigenfunction of the eigenvalue problem, because for self-adjoint form, they form a complete set. So again, G R prime or G R sub 1, R sub 2 can be written as sum over all the eigenfunction by right? In R2 lambda n, just like what we did before, and then obviously that implies G R1 R2. If you interchange, then you get the complex conjugate. If they are real, obviously they will be the same. Okay, so that's here generalization, right? And again, this to solve for G, we actually need to solve for the differential equation as L operator G Y02. In that case, that equals the delta function. And these are three-dimensional delta functions, which means it's you have three multiplication of three delta function in single value function. I mean scalar function, right? And okay, and now to solve that, again, there's different method. You can solve it in different coordinate system, like a Cartesian or cylindrical or spherical function. Spherical coordinate, and use at least some part of the delta function written in the coordinate system can be explained using some orthonormal function like Bessel function or Legendre polynomial or spherical harmonics, that kind of thing. And then leaving one delta function and solve the green function like what we did for the 1D problem. So that is one way to do it. And so the green function will involve some expansion in some orthonormal basis. But then another part will be similar to what we got from section 1. Another way is to solve it in total vector form. Just solve this equation in just like a vector equation, and some simple operator that can be straightforward, like simply a Laplacian. For Laplacian, then you don't have Q, you just set P equals to 1, right? That's just a Laplace equation. Or with the right-hand side, that becomes a Poisson equation, right? But the Laplace or Poisson, that the green function is the same, right? And it's just basically now, if for this particular problem, we can set L as Laplacian itself. Laplacian. This is on L sub 1. G equals the delta function. Okay, and that turns out to be straightforward. I have 10 minutes to do that. Actually, not that difficult, because again, we can use the similar method, so as what we did in the last section. So consider R1 not equals to R2 first, then Laplacian G will be 0. It's basically just a Laplace equation, right? And now we consider a symmetric case, because there's nothing not symmetric, because this is just a vector difference between R1 and R2. You consider this as just like R2 is your reference point, R1 reference to R2 is isotropic in all space. So like you draw a diagram. So if you have R sub 2, this is your R sub 2, right? Whatever that is. Then this is R sub 1. And this vector is R sub 1 minus R sub 2. Right? And the delta function is when R sub 1 minus R sub 2 is 0. So basically, this is for this choice of R sub 2, this is your origin. right? That is the delta function is 0, right? But relative to this point, and all directions are the same. Or this isotropic with respect to this choice of R sub 2, right? So in fact, you can actually define this as your polar coordinate. This is your new polar coordinate. Then you expect the solution to be spherical symmetric. Depends only on the magnitude of R, this R vector. Okay, so that is just from the property of the problem. And for this particular problem, you consider the infinite space, consider all space, and you let maybe impose a boundary condition G goes to 0 as R goes to infinity. We also require that. Right. In this case, using this new coordinate system R, it's basically changing the Laplacian using R sub 1 to Laplacian in R, right? That and R1 not equals to R2, the Laplacian R is equals to 0, right? So R is defined as this R1 minus R2. Okay, and now assuming this is isotropic, then the differential equation is straightforward. That's the speaker one. I think it's the textbook didn't have that. I mean, this should be a step. So it should if you write in explicit derivative in coordinate system, so d square. I think that linear term should have a factor of 2. Right, and then you don't have the derivative in phi and theta. That would be 0. Okay, and so what is the solution of this one? So you can try. I mean, there's that. I mean, you can try a certain form and see if that is the solution. See if G is proportional to some constant divided by R. Let's try, because we already knew this. This should be the solution, right? Then this implies dg dr is minus c over r squared. B squared g r squared is 2. Right, minus 2. Is it 2? Yeah, 2 the R cube, right? And why didn't I get that seems. Oh yeah, you divide it by R. So, but this is going to here. This divided by R multiplied by 2 goes to 0. So that would be d squared g dr squared is plus 2r dg dr. This 2c r squared r cube. This 2 multiplied by 2 divided by r is minus 2c r cube. Okay, that is 0. So this you see that this is a form, and this is in R. So in our cases, R is R1 minus R2, the magnitude of that. So you can say that G equals to some constant divided by R1 minus R2. And now the rest is just to fix the constant, because we are not considering R1, we are considering outside this point, R1 equals to R2, right? And the, to determine the constant, we're actually using this solution approaching this point. We try to get the get the volume, little volume, including this point, and go back to this equation, and not just the Laplace equation with now you've got some equation using a delta function, using that and try to see if we can fix this constancy. Okay, so that what we will do, and no, this is just to get this form, so get rid of that. Now the idea is that now we solve Laplace equals to delta R, or actually it's delta R vector because this is a vector. Okay, now just like what we did in the last section, we integrate over the delta function. In this case, we integrate over volume of this delta function. Okay, so you see a little volume, or we can say this radius delta, the over the integrate over volume. The volume argument is 4 pi r squared dr, right? And integrate from 0 to delta, right? And obviously, this is a 3D volume integration over a 3-dimensional delta function. If this volume contains the delta function, that's equals to 1. Is that okay? So that is the requirement how we define delta function. Now we do the same thing over the left-hand side. This is dv. Okay, let's write it out explicitly. And again, that is 0 to delta, but we can write it as this divergence. Laplacian can be written as, actually, I can keep the volume integration first. Divergence of gradient g and dv or dqx. Right. And over the same little volume, right? So what we want to do is use the divergence theorem. This becomes the area integration grad g dot n a. Okay, so let's write down this origin is r equals 0, and then you have a spherical volume v. We require that there's a radius delta, right? And then obviously n is just the radial unit vector n, and then we do a surface integral over this surface area. Okay, and then what we want to do is this gradient g. So g is given by g is c over r. What is gradient g? That's gradient g. Should be just d, right? Just ddr, right? And then r direction, right? So it's minus c r squared, right? Yeah. So that is that's gradient, and then we evaluate on the surface. The surface is a radius as delta, right? And so, and then we require that dot n is just r, so r dot r unit vector, so it's just 1. So basically, it's dA over this quantity, but r is fixed in here. R is just delta. So let's just keep writing it. So you have c. R is just delta. You have delta square. And you have a minus sign, right? And then what else? And that area integral is over this surface area. The surface integral is Just basically everything is just dA now. It's just everything else is just dA, right? Yeah, that is minus c over delta square and 4 pi delta square minus 4 pi of c. And now that equals to 1. Why is it 1? Why is it there's a negative sign? Why did I get a negative sign? You see why I got the negative sign? I got the minus. I'm actually over time. No. The G is, I think the G is right. The G is of this sign. G is, oh yeah, G is actually negative, defined as negative. So it's correct. I, I, I take it back. So actually G is a negative sign because, I mean, sometimes just remember the different convention. People define the green function differently, sometimes with a negative, sometimes without a negative sign. So this implies C is equals to 1 over minus 1 over 4 pi. The G is minus 1 over 4 pi. X, R minus R1 minus R2. So that is the final. Wonderful. Okay, but this is your equation 10.43. Okay, and some people have the positive sign, like I said, then the equation with a negative sign over the right-hand side, and then some people have no 4 pi factor, just 1 over r minus r pi. And in the integration formula, you add the 4 pi. Okay, so but anyway, that's how you get the green function for the Laplace equation. Okay, and there's some homework problem for you to generalize that. But I need to stop now because